Yes, now it is being recorded. I was looking for that because if this meeting is being recorded, that will be important for you to work on the cadence in future, right? Now, what we will do over here is that we will go to the file. We will make a new library. In this new library, I'll give the name to this library. Uh, Let me give it a name that I need to work with workshop underscore Ashish. Or I do not use any special character, I use workshop Ashish. And then there is an option attached to it existing technology library. Whether you wish to work in 180 nanometer, whether you want to work in 90 nanometer, whether you want to work in 45 nanometer, that is decided from this. I'll click. Then I'll press apply. And there you see a window that asks you that which library you wish to work with. You want to work with GPDK90. GPDK is Generic Process Design Kit, which is called the model file. In which technology you wish to work. There can be a 90 nanometer, there can be a 45 nanometer, there can be a FinFET. Let us start working with 45 nanometer. And then we'll press OK. You will see that somewhere over here, you have started seeing the generic 45 nanometer PDK, right? And then you will do apply, okay. Then you file new, you have created a library, now you will create a cell view of which, like in which library you want to create a cell view. See, there are the libraries. In libraries, you have the books. It is like that only. First, you have created a library. Now they will ask you that where you want to create this new book. I select Workshop 45, Workshop Ashish. And remember, this is a 45 nanometer library, right? Now I name the cell, which is called NMOS. NMOS characteristic. NMOS character. See, it's a view schematic, type schematic. You can have these different sort of views. You can have a Verilog A, Spectre, schematic, H-Spice, but we are working on schematic. Schematic is something where you can actually see the transistors. Okay. Now you see this sort of a window. There you have many options. We'll keep on learning these options one by one. But before that, I am going to press I on my keyboard, which means new instance. This type of window will appear, add instance, and then I'll browse it. Now I wish to see a transistor, which is NMOS. I want to see the characteristics of NMOS. But because my library is of 45 nanometer, I can see a transistor in analog library also. I can see a transistor in GPDK 90 nanometer also. But my library is 45 nanometer. So I'll work with 45 nanometer and I'll see there are different NMOS here. This NMOS 1 volt, NMOS 1 volt HVT, NMOS 1 volt LVT. I'll show you everything. See NMOS 1 volt and then symbol. Close. You see its length is 45 nanometer and its width is 120 nanometer. Right? And then once you hide it, you get this transistor. Place it anywhere. Press escape, the other transistor will go. You see there are 4 terminals as I told you in theory. One is gate, one is this drain, this is body, this is source. Now I'll put the wires to all its parts. This is the wire. and I'll connect this body with source. Tomorrow I'll explain you why I've connected the body with source. You please see how this looks like. I can enlarge it for you. I hope it is visible to everyone. If you have any doubts, any queries, please write in the chat box. I'll try to reply. If you feel like you are not getting anything out of it, I'll repeat. Now I'll again press I, go to browse in analog library. What I'll search ground. This is a ground. There is a symbol, height, and you get a ground. Then you need a source, voltage source. In analog library, you look for voltage source, VDC. Here you have VDC. There is a symbol, close. Then it is asking for DC voltage. How much DC voltage you want to give it? Let me say I wish to work with 0.6 volts. Or maybe 0.8 volts. It is showing VDC 800 millivolts. And I'll give ground to it. This is a voltage at gate. Now I'll see the voltage at drain. Press R for rotating, C for copying any symbol, R for rotating. And now this is your simple NMOS circuit is ready, where you can see input and output characteristics of MOSFET. I'll show you how this input and output characteristics work. Go to launch. Is a first very simple experiment of Cadence that I'm showing you. Tomorrow, whatever we'll see here, tomorrow we'll discuss in the theory class. ADEL. In this ADEL, let me make it small so that you can see it clearly. You go for outputs. Which output you want to be plotted? Select on design. Which output you want? When you see the characteristics, let me tell you. In the characteristics, okay, so I'm not getting that particular point for that showing it, but no worries. Yes, you see, if you click over here, this point, you will get a drain. What are the output characteristics and what are the input characteristics of MOSFET? These are the output characteristics. These are the input characteristics, right? In output characteristics, you have VDS over here and ID, drain current is here. In input characteristic, you have VGS, gate source voltage over here and drain current over here, right? So I'll show you how to do. Okay, so if you see here, I want to see the output to be plotted. Select on design this point. Let me enlarge it. Output to be plotted this point. This. You see the circle over here. Now you see in ADL you have NMOS drain current, right? Now you see you have to plot the DC characteristics. This you will select the component variable. Select component. This is the, see what is VGS? But tomorrow I'll tell you VG minus VS is VGS. You select over here VGS. Let me give it a Y volt over here. And X volt over here. Now in this, you will have to select a design variable. VGS is X. Select the design. VGS is X or Y? VGS is Y. From where? 0 to 0.8. Apply. Okay. This does not represent. You select over here. Name Y. Value 0.8. Apply. Now it will take a while. This is a DC analysis. Now you will use the value of X. This. Now when you plot this, it is saying there is certain error that you are working with 90 nanometer file. Yes. You see, this is the input characteristic. When you have VGS over here. And if I try plotting, what is the value of the VDS for this? This is 0.8. You have taken, see, let me explain to you. You have taken 0.8 over here, 0.8 over here. Now this Y is here 0 to 0.8. And this is being plotted for the value 0.8 of X. Now if I take different values of drain current, how I'll do that? I'll go with parametric analysis. X from 0 to 0.8 with 9 steps. You see here. You see the result now. For every value of drain current, see the drain current over here is 0.1 volt. See, it is written that X is equals to 0.1. I hope it is visible to everyone. Here the X is 0.2, means drain voltage is 0.2, 0.3, and this is up to 0.8. You have all the characteristics of input with respect to 0.8 volt VGS. Now, if I change this variable name to X, and now X is varied from 0 to 0.8. What is X? X is voltage at drain. If I take this drain in the axis, then it will be the output characteristic. How it will look like? This is the output characteristic. And if I try for different values of gate voltage, how this will look like? Let us see. See, this is for 0.8 volts of gate current, gate voltage. This is 0.7 volt. This is 0.6, and rest are below 0.6. So that is how you plot input and output characteristics of NMOS. If you are not well conversant till now, please let me know. I can explain this process again. Or if you have any doubts still here, please let me know. Otherwise, I'll explain you that what are the high voltage transistors, what are the low voltage transistors, and how you can see them in your cadence. Please let me
Hello.
know. Yes, 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 please.
Hello. Sir, you have selected like a DC voltage and ground from analog terminal. So,
Yes.
and you also mentioned that they are available in digital also. So, is any difference with analog and digital? Means like for digital, it is fixed 5 volt, and for analog is something kind of difference?
In this, what happens is that if you see all these libraries, this is GPDK, this is generic process design kit. This is for selecting the MOSFET as a capacitor, MOSFET direct, MOSFET as a resistor, low threshold voltage, high threshold voltage MOSFETs, but you do not have the base components in GPDK file. GPDK file means whatever you can design on the silicon wafer, that is GPDK. But when you have to give the external circuits like wire, VDC, ground, these are to be connected from the analog library. Whether you are working with any of the circuits, maybe of analog or maybe of digital, you have to take these external components from the analog library and your MOSFET and related to MOSFET components from GPDK, that is generic process design kit library. This is a basic difference. GPDK का ये मतलब होता है कि आपने अगर 45 नैनोमीटर ट्रांजिस्टर पर काम किया तो 45 नैनोमीटर ट्रांजिस्टर जो है वो एक वेफर के ऊपर थ्रू आउट एक जैसा रहेगा. सो एवरीथिंग विल बी ऑफ 45 नैनोमीटर. दैट इज व्हाई यू यूज जीपीडी के 45. ऐसा नहीं है कि वन ट्रांजिस्टर ऑफ 45 नैनोमीटर, वन ट्रांजिस्टर ऑफ 90 नैनोमीटर, वन इज ऑफ 180 नैनोमीटर. नो, if one transistor is of 45 nanometer, everything is of 45 nanometer. Every MOSFET component is. But these components like external supply, which is called VDS, external ground, or any wire, it has nothing to do with this semiconductor nanometers. That is why I have taken it from analog library. I think I have given the question of your answer. If your question is something else, please let me know. Any query, anyone, please.
And sir, one more question. Right
Yes.
now, you are showing all these simulation part. So
Yes.
any version is available so that we can also do the same practice on our side.
Yes. Either you have it. Give me a second. So my other question, my other point is that I think I should change the window before explaining all these things. Uh, Now, please see what we have done today. I'll explain you in a very short process. Now, please see what we have done today. It is like I have taken a MOSFET. Here I have given some voltage. See, this is gate, this is source. Because source is at ground. Ground means 0 volt. If I give 0.5 volt over here, so means VGS is VG minus VS. So VGS automatically becomes 0.5 volts. I hope it is clear. If I've given 0.5 volt over here, VGS is VG minus VS. Now I have given 0.5 volts over here. Now VDS is VD minus VS. Now because VS is on ground, so you have 0.5 minus 0, so it is become 0.5 volt. When I see the characteristics of MOSFET, there are two types of characteristics. There are input characteristics, there are output characteristics. In these characteristics, here you have the VGS and there you have the drain current. There you have the drain current and there you have the VGS. Oh, sorry, VDS. Please remember your VGS is equals to VG, VDS is equals to VD because your source is on ground. Now what we have done is we have taken the ADL window, analog digital library, and in this ADL window, I have selected drain current as output. Then I said that I will be selecting in my DC analysis, I can select my this x-axis. I selected my x-axis from 0 to 0.5 and this y-axis drain current is to be computed. And then when I simulated it, I saw that this sort of a graph appears. And if in the DC analysis, I take VGS over here. I have taken this as X and this as Y. Now, when I select my Y from 0 to 0.5, I see this sort of a plot. Remember, whenever I go for the input characteristics, it means there is gate voltage, gate source voltage is on the x-axis, and when the drain source voltage is on x-axis, it means we are going to see the output characteristics. Tomorrow in lecture, I'll explain you what is the meaning of input characteristic and what is the meaning of output characteristic. In input and output characteristic, it is very important to understand for a student who is to work on the VLSI that you see that in this, there is very low current till this point. But the current suddenly shoots from here. This. The thing that we will learn that why this happens. This is very important concept that one should learn why this happens. Similarly, in output characteristics, we will see that till this voltage, we have seen the linear increase in current. But after this linear increase, the current gets saturated. For all the students who are going to work in the digital VLSI design, we all work in this domain only. Why? Because we say that in the whole process, the current is constant. However, actually the current is not constant. It is slightly increasing. But if you compare it with this part, it is almost constant. So the output characteristic tell me that after which drain voltage my current will get constant, and input characteristics tell me that after how much gate voltage my current will shoot like exponential thing. That is why I study input and output characteristics. See, please understand this. Until unless you do not know the character of a person, you cannot make him the part of your team. It is very simple. If you do not know the character of a person, you cannot make him the part of the team. That is why you need to know the character of your MOSFET if you want to make it the part of your the designs. So I would encourage that you please simulate them, see their wave shapes. I'll give you all these recordings so that you can recreate what we have done in the class and these lectures also. But I would request that if you have any query that comes up to your mind, please ask in the class, because that will also open up the mind of my mind and the mind of the other people who are listening to this lecture. It is a very important part. Now, if you have any doubts, please let me know. Otherwise, we'll close it here. And tomorrow we will do the characteristics of PMOS, or we'll make one simple inverter. Any doubts? Right. So if you do not have any doubt, I'll close my lecture over here. And tomorrow, because tomorrow there will be no introduction, nothing, we'll study more intensively, and we'll try to incorporate more practicals and a bit more intense theory part. Please revise it. I'll give you the recording by, if not tonight, by early morning today. Please go through it, revise it. I'll give you these notes also, and then let me know if you have any doubts. Tomorrow we'll start with your doubts. Right? Thank you for joining. Thank you, everyone. Thank you so much. We'll continue from here tomorrow.